This is a hip implant. For about 1 in 10 of you in this room right now, there is a very good chance that you will have to have one of these implanted within you in your lifetime. Yes. The main risks remaining today for having a hip implant isn't the fact that it can loosen or that your body can reject it. The main problem that we face today is infection. Now, for any surgery you get today, infection is always a risk. But for hip implants, it's a little bit different. When you think of bacteria, you think of small individual cells floating about your body, multiplying, dividing, and spreading their infection. But on a hip implant, they stick to the surface. Not only do they stick, they begin then to spread. They secrete fluid that acts like a cement, which allows them to build up and basically create a mini little fort. These forts are what we call biofilms. Biofilms are particularly dangerous as they are tolerant to antibiotics with this newly formed fortress. Not only that, they also have a big problem where they're able to stick, like Weetabix to the side of your cereal bowl in the morning. And if you know anything about getting that Weetabix off the cereal bowl, it requires surgical removal. And now so does this hip implant. Even after you get it removed, the hip implant, whenever you get a new one in, has a very high chance of becoming reinfected. Complications due to infection can also cause fatalities. And the antibiotics that we use today are actually becoming less effective. We're running out of medicines and we're losing the battle against bacteria. But what if I told you nature already has a solution? Researchers today have found when they look at the surface of dragonfly wings that there are tiny little spikes on their wings. And what happens is when bacteria tries to come along and attach, it pops like a balloon on the back of a hedgehog. It's not just dragonflies that have this effect. We can see this in shark skin, on lotus leaves, and even on some kinds of seaweed. Nature finds a way and life finds a way. In my research, what I'm trying to do, I'm trying to change these surfaces of metals to kind of replicate these surfaces we see in nature. What I do, I use laser surface treatment at a very high power onto these surfaces with high precision to create these surfaces. It's been working so far. There's definitely some challenges to overcome, and there's a lot of unknowns that we need to explore. As an engineer, I feel very privileged to be working with surgeons alongside them to try and improve healthcare. And what I think is that we do not need to be developing new medicines or new antibiotics. We need to be taking inspirations from nature to create better devices and better designs and to be victorious in the battle against bacteria. Thank you.
Thank you very much, Ryan. Hello.
What was that?
Nice shirt.
Oh, thanks. You like it?
Yeah, that's great. That was brilliant. That was
Thank you very much.
very enjoyable.
Thank you very much.
Yeah, I don't know if there's any copyright issues there with the fact nature's done it first, but can we go to the Francis Desperadass?
Yeah,
Yeah,
that's right. The person from the pharmaceutical company straight in.
Oh,
there. No, Ryan, thank you for that very engaging presentation.
Sure.
My question is, I have a few questions, but the one I'll go with is, the work that you're doing with surgeons, have you got to clinical studies yet?
Absolutely not. This is a very low technology readiness level, and to be quite honest, we do not fully understand the method by which bacteria attach to these surfaces in the first place and what the kind of zones are in the implant that they attach. The surgeons that I'm working with down in Musgrave, we just initially sort of got some work set up. They're going to hopefully start, there's a lot of red tape to cross, but they're going to hopefully send me some of the extracted implants and we can identify the zones so that we can target the kind of surfaces that need the treatment in the first place.
That is amazing. Thank you so much. Yes, Aaron, go ahead.
So, fascinating. Really interesting to hear about this. Question of technique of, it's not on my side, laser engraving, not quite the correct way of putting it, but the laser to make this surface
Texturing, if you want to say.
Surface
Sure.
texturing, thank you very much.
Yep, now there's lots of different ways that you can use a laser in this. Sorry, am I?
No, you maybe predicted it, so go for it.
Sure. So,
Locality, scalability, all that kind of stuff.
of course. So the main issue is whenever you're using lasers to create the kind of little nanospecks that I mentioned there, those require very, very powerful lasers, like a femtosecond laser, certain kind of wavelengths. I need a little bit more funding before I can get my hands on those. Any collaborators? what I use at the minute is basically fiber laser. And what I'm working with as well is 3D printed titanium, just to throw another layer in the complexity there. That's got a very rough surface whenever you 3D print it. And we need to basically remelt those particles because they're such a large scale. So it could be a multi-step process if we need to as well. Sorry, I kind of tangented there with that there, but yeah, hopefully that answered it.
You got my second question about 3D printing.
Ah, there you go.
Yeah, so originally aerospace.
Yeah, that's right, yeah.
So why?
I know, right? Basically, whenever I went to kind of decide to do engineering, I had actually initially biochemistry, chemical engineering, biomedical engineering, lots of different ones. I just like working in engineering and just solving problems. The thing is as well, in aerospace, you use titanium in a plane, you also use it in your hip. So the same principles that you're kind of getting from materials there are the stuff that we can apply, that I was able to kind of apply into the biomedical side. So yeah. Hopefully that's answered that. Okay, sure.
Fantastic. Oh, it's turned off. Thank you very much.
Oh.
A round of applause there for Ryan. Thank you.